Everything is being influenced by code written by developers.
At some point, you're going to wake up and say, what the hell am I doing?
It's hard to believe. It's the largest group I've ever been in front of, I think.
We develop the future.
Hello everyone and welcome to another We Are Developers live session. I'm Benedict and I'm so glad to have you all. As you may have already read in the title, today is all about machine learning, a very interesting field in the artificial intelligence with the goal to imitate human behavior. But before we start with this session, I have some wonderful news to share with you. The We Are Developers World Congress is finally back as an in-person event in Berlin in June. So don't forget to go after this session to worldcongress.dev to get further information and also to get your tickets. Also, feel free to interact with the chat to your right during the talks, and don't forget to submit some questions as we will have a short Q&A after each talk. But as always, be friendly to each other, respect each other, and keep our code of conduct in mind. Here's a short video about it. So, right back to machine learning. And I'm so glad that we have three wonderful speakers today. And let's start with the first one. He is a senior data scientist at Cariad, which is basically the central software company of the Volkswagen Group. He has a degree with a major in informatics and research focus on artificial intelligence and robotics. And currently, he's responsible for AI technologies at Cariad. Please welcome with me, Nico Schmidt.
Hi. Hello, everyone.
Hi, Nico. Wonderful to have you. How are you today?
I'm fine, thanks.
Perfect. Would you mind asking me where you're joining us from today?
I'm in Berlin, Germany, and that's where I live, and I'm sitting in my home office currently still. We are now allowed to go to the office back, but I'm not used to it, so I have to find a way and have to find my office.
It's a strange environment, no?
Yes.
Okay, let's jump right back. Would you mind telling us what you're going to talk about today?
Yeah, so I'm talking about intelligent data selection for continual learning of AI functions. So I focus on machine learning functions, and I have a strong focus on autonomous driving perception functions or advanced driver assistance perception functions. And I will go into the different use cases we have if you think about data selection, the different methods we could apply, and also then later on show you an example, plus a hint on how we generate a uniform framework for data selection to be applied to the customer fleet.
Nico, that sounds very interesting. You got my full attention, and I would say the stage is yours.
All right. So thanks everyone for joining, for listening in. So this talk, as I said, is about intelligent data selection for continual learning of AI functions. And I will first guide you through the use cases. What is data selection with respect to machine learning models, and why do we need to do it? And which methods do we have at hand to achieve it? And then I will give you an example use case where we use softmax-based uncertainty estimation for data selection. And then also show you how we deploy this to the fleet and try to build a unified, universal data selection framework that our perception teams or basically all development teams within Cariad that have data requirements can use to deploy their to collect data using the customer fleet, and then hint on the challenges that come with that. Right, so first, what is data selection in machine learning? Which use cases do we have, and which methods are existing? So if you think about data selection in AI functions, the most basic thing you always do if you want to train a model is, of course, you need a data set, right, for training and for testing. And this data set should be as diverse as possible. With that, I mean, with respect to class statistics or traffic scenarios, if you think about autonomous driving, but also about regions where we want to deploy the function and environmental conditions like weather, seasons, and so on. This should be as much as possible diverse as possible, so that we cover a large application space, right? And for testing, also make sure that this works everywhere where we want to deploy it. So then the next step is basically what we call active learning, where you iteratively train models and then find data that improves the model's performance the most. And then we can iteratively select new data, add it to the training set to refine our model and make the model better over time. And that's a major scenario here, but we also can look at corner case detection, for example, which is more a case for production use, where we want to detect the boundaries of our model's operational domain, right? Because we, and especially in safety critical applications, have to make sure that we have appropriate measures, we take appropriate measures once we get outside of our operational domain. And thus we need to detect this. But also in terms of data collection, it's interesting to record those situations, because then we might improve our models and push those boundaries and broaden the operational design domain. So finally, if we think about creating completely new perception functions, we also need to do data selection, or want to do data selection. But this could also be extending existing functions to new domains, right? In these cases, we want to create new data sets with, for example, scenario-based triggering of the recording, or specific retrieval methods. And I will give an example later on. So let's talk about where do we have data sources, right? Where do we have our data? So usually we store our data in some kind of storage, might be cloud storage or on-premise data centers, where we have a data lake and store the maybe data that we have recorded in the past, for example, or there are public available data sets one can use or buy, actually, and then we can have this all in our data centers. Now, of course, regarding scenarios, this is kind of limited, right? This is always specific to certain scenarios we previously recorded somewhere. So also this data is what I call classic data, because it could be from the past. It's not the most up-to-date data. If you think about, the world is changing all the time, right? But what the positive side is, in the data lake, of course, we have in the backend, we can attach heavy compute clusters to our data lake, and thus have heavy compute capabilities in place to process the data. And this also enables us to do batch selection, so we can look at the whole data distribution at once, to make reasonable selection. So now, if we think about our testing fleets we have at hand, we can of course send them out to go out data collecting for targeted scenarios, right? And there you usually have something, for example, like a scenario catalog that the test drivers get. So they are sent out to specific regions, maybe at specific times, and to collect data. So this data is, of course, up to date because it's newer, right? However, if we want to do data selection right in the car, we only have moderate compute resources. I mean, it could be, if I think back in the past, doing test drives, we had we could in the test vehicles fill the whole trunk with computers, right? We can have heavy workstations even with GPUs inside to do some computations. But it's still not as heavy as in the data centers, of course. Another thing is here we now have a stream-based selection. So we get the samples one by one, or the snippets, and we cannot look at the whole distribution at once. We have to make a decision in a certain time range. Do we want to record this or not? And this is, of course, a different problem. Now, the kind of holy grail in data collection is, of course, the customer fleet, because the customer fleet is the largest fleet, right? Volkswagen has a huge fleet out there, a lot of cars all over the world. So we have access basically to what I call the open world, to every possible scenarios, more or less, right? And it's not limited like if we go on specific test drives. And it's most instant. It's the most instant snapshot of the current situation out there. It's the most up-to-date you can get. However, of course, our series cars, they don't drive around with heavy workstations in the trunk. Instead, they have ECUs with limited compute capabilities. So whatever data selection functions we deploy there are limited in their compute capabilities or resources. And we also have the stream-based selection, the sample-wise selection approach here. Okay, so what is informative data? What data do we want to record in the end? So for this, it's nice to look at the long-tail distribution, where we see that the probability of occurrence is usually very high in common traffic scenarios, right? So most of the time we drive around in very similar situations, and from this we have a lot of data. Thus, also our models perform well on this because that's the best covered data in our training data sets. So what we want, what we see as more informative, is the more rare scenarios, where we have maybe safety critical scenarios also, but also rare objects and stuff like that, because here our model has the most capability to learn new things about its task. So this could be, for example, weak or noisy sensor signals. If you think about difficult weather conditions where objects are not easily visible, that might be good for our model to learn that this is also existing and refining its capabilities towards this. But we can also have atypical class distributions, for example, crowded scenes of certain classes that is usually not the case on the street, and also not represented in our training data so far. This would be something that would be interesting to record to help our models or improve our models. Same goes for very rare classes, so classes that we don't see often on the streets, and that are underrepresented in our data sets usually. And last, we have situations where we might have context mismatch. So we know the objects, but somehow the constellation is weird and doesn't really. It might confuse our existing models. So how can we achieve this? How can we select those rare cases? There are different approaches out there in research and application. The biggest class, I would say, is the uncertainty estimation methods class, where we try to estimate the uncertainty of a model with respect to its own predictions. So, for example, we can look at the softmax scores of a machine learning model, which is the most naive way to do uncertainty estimation, but is already providing some good results, as we see later. We can also deploy more sophisticated methods like Monte Carlo dropout, where you use a dropout during inference also, to, instead of only get a single prediction, produce multiple predictions with different dropout configurations, and thus you can have a mean prediction, but also next to it, in addition, the standard deviation of the predictions, which gives a measure of how difficult, how uncertain the model is about the scene. And there are different other things like metasec, very interesting methods out there. So then we can, of course, also look at the temporal domain, right? If you look at successive frames, we might compare the predictions of our model from one frame to the next and see whether the output prediction is stable over time. And if it's always the same prediction, then it might be a hint that this is a simple scenario for a model. But if this is fluctuating a lot and the model is flipping between classes all the time, it might be a hint that the model is still uncertain about it and has problems with this situation, and it might be worth recording it. So then in the anomaly and novelty detection class, we usually have something like density estimation or clustering of our input space that then allows us to, if we receive new samples, map them into this density and look up how dense the area is around this sample. And if it's a high density region, it might be that this sample is not so interesting to record because it's something that is well covered in our data set. However, if it's somewhere in low density regions or outside, then it's a hint that this is something special and or anormal, and we might want to record it to include it into our data set. And then we have ensemble methods where we can have different models doing the same task. And those can be different architectures, for example, or the same architecture models, but trained with different data portions. And so then we can look up whether all of the models agree on a sample, so whether all they have the same prediction. Or if there's a mismatch, right? If the models disagree and have different predictions for the same image, then it might be also a hint that this image, there's something special around about it, and it's difficult for the models to predict. All right, now let's look at an example we used where we have softmax-based uncertainty estimation for a traffic light detection task. So in this example, we have a model, a detection model that receives images as input and produces or detects traffic lights in them. So now we apply our uncertainty trigger that is internally using the softmax to calculate an uncertainty score for all of those different components. So we basically have for all the detections we have here, we assign an uncertainty score to them. And then have some that are very low uncertainty, where we have well predictions, but also some that produce high uncertainty. So now we can aggregate all of those components to an image-wide trigger signal, which means if there's enough aggregated uncertainty in an image, we want to record it. And if there's not so much, then we just discard it. So here's an example how this could be looking like. So here the traffic lights above here are very well detected. So not so interesting, but here we have a traffic light where the detection uncertainty is very high. And here we even have a taillight of a car, which is detected as traffic light, so it's a false positive. And similar here, we also have a false positive, or a traffic light very far away, difficult to detect. So this is these are things that are counting into the aggregated score, and where we might want to record those samples to include them in our training data set. So now to evaluate whether our intelligent data selector is actually performing well and selecting the right data, we do an offline experiment where we first have a labeled data set that we split into different portions, and we have a training set, training and evaluation set, which we use to train a model, and then we apply this model to a selection pool, and the selection pool is basically from there we select, using our intelligent trigger, we select a new portion of a data set which has the highest uncertainty images, and those we use for refining our model. So then we apply this model to a test set. We have two test sets here. I come to that later, to calculate the KPIs to measure the performance. And now we want to make sure that this is really a better way than just going out and randomly collecting data. That's our comparison baseline here. So we do the same experiment with throwing a dice or a biased coin, basically, to decide whether we record a sample or take a sample into the new training set or not. And then we do the same story. We refine our model with that new data set, and evaluate it on our test sets and compare the KPIs. So let's have a look at the results. This is basically forming a one-step active learning experiment. We did this 10 trials in this experiment here. And we have our initial model's performance, which, of course, because the model was trained on a small portion of the data, not so high accuracy or IOU in this case. So the performance is getting better if we add new data for both experiments. But we see that using our uncertainty trigger, we get better performance increase than using our random data selector. And the same we see also in the precision recall curves here. So now it's very important to think about how to properly test our improvement, how to really benchmark our new models. So for this, as an example, we have, next to the randomly generated test set, we also include a test set where we have corner cases oversampled. So this test set really contains mostly corner cases. Difficult images for the model. And so we apply both our trigger methods on both test sets. And what we see is that for the random test set, our model, so this was one experiment we did in the past, our model didn't really make a big difference on this test set. However, on the difficult cases, we get a larger improvement here. And we also have a visual perception team in Cariad that did similar experiments, and they splitted this up, this analysis, with respect to scenarios. And now that's very interesting, because if you look up in this column here, the relative selection frequency, this means how many images or portion of the images have been selected from each scenario. Compared to the random selection case, we see that our intelligent trigger selects more of the nighttime images and more of the city images, which kind of makes sense because these are usually the more difficult cases. And it selects less of, for example, rural roads or highways. But this also means in the resulting models that we might have performance reductions in those image. While we get better on the difficult ones here, we have some performance reductions on other scenarios. So it's very important to not only look at the random average, but to really have the benchmarking being more detailed to really make sure we get the improvement we actually want in all the situations we want. And this brings me to another short hint on this project called KI-Absicherung, which is a research project which we do with different industry and university partners. Here we not only look at performance KPIs, not only pushing the mean IOU, but we also want to evaluate for safety, right? So what we do in this project is we generate methods, measures, and processes to verify AI-based functions for automated driving. So this means from this project, we might come up with a catalog of metrics that are important for safety, and we need to include those also in our benchmarking in the end. All right, now let's see how we deploy this trigger now to the car and use it for closing the big loop. Namely, we have in the vehicles our ECU and the protected area there. We have a module running called we call it Instinct, which stands for In Situ Intelligent Data Collector, and this is where we deploy our trigger functions in. So this basically acts as a filter, you can say, to reduce this huge amount of data that cars generate, to only pick up the informative data and let that through to be uploaded to our cloud infrastructure. And then this can be used for refining the models, for example, and deploying a better version of it back to the fleet. So let's see how this looks in action. So what you see here is on the left side, the input images that the car receives. And then in the middle, you see the pixel level activation of our traffic light detection model. So this is basically where the predictions that, the predictions that the model gives. And on top of that, on the right, you see the uncertainty estimates that our uncertainty trigger creates. So for each prediction, you see here a number in the bounding box. Plus here in the title of the figure, you see the aggregated score of the whole image. And this can be between 0 and 1 in this case. We normalized it. And it can be, now we can set a threshold and say whenever a certain threshold is exceeded, we want to record this sample. So here you see another snippet where we are approaching a traffic light. It's very far away. You cannot barely see it as a human, but the model picks it up. However, with a high uncertainty, it's very uncertain about whether this is really a traffic light. So now our uncertainty score exceeds a certain threshold, and the image is triggered for uploading, right? And this one image we want to keep. So then if we go a bit further, we approach the traffic light, and there are more traffic lights coming in on the side that we pick up, which have also high uncertainty. Plus, what you can see here is we have a false positive actually on this traffic sign here, which gets also high uncertainty and adds to the score here, which causes our image here to be uploaded. And then as we approach the traffic, the crossing, the detections get better, and we get more confident about this detection, so there's no need to record it. So that's basically the major story. It's not about what we collect or which samples we really upload. It's about the large amount of data we discard, right? There's a lot of data that we don't need to record, and this wouldn't add any benefit to our training. But we only focus on the really difficult cases here. So now let's think about another scenario. We have this traffic light detection model developed in Germany, trained with German data and deployed to the fleet. Now we want to also our US customers to enjoy this new feature. So we take our model and deploy it to a part of the customer fleet in California. And now, of course, in California, a lot of things are different, right? The vegetation is different. The lighting conditions are different. We have different weather, but also the buildings, the road, in part maybe the cars, but of course the traffic lights look different. And this poses challenges to our current model, right? The model is performing not so well, but I mean, it can pick up several traffic lights, but usually here we have those large bars that are on the other side of the street, very different than in Germany, and the model has never seen this. So now, using our trigger function here, we can detect in which situations this model has problems with the prediction, and then record only those parts to create a new data set to train a model specifically for this region, or to take our existing model and to expand the operational design domain also to this new region where we want to deploy it. And here I want to have a short hint on another research project we do with industry and research partners. It's called KI Delta Learning, where we aim at scalable AI for automated driving, and we look at a lot of different deltas that can occur during development. For example, if you think about synthetic to real, different locations, different time conditions, or different sensors. And in this project, we also create new methods and tools for the efficient expansion of our current existing models. Beyond the pure data selection, we also have transfer learning methods and so on. Okay, now having said that, I want to show you how we now want to build a universal data selection framework for the whole company to enable all the teams that might want to collect data for their specific use cases using the customer fleet. And this brings a lot of challenges with it. So what we aim at is a trigger plugin framework where you can put in different triggers into our Instinct module. Those can be, for example, uncertainty-based triggers, diversity-based triggers, novelty-based triggers, or could also be logical triggers. If you think about traffic lights, then why not just looking at our GPS position and looking up in a map whether we are close to a crossing or a traffic light, and then record there, right? So this is also possible, and we want to enable to have all those triggers running side by side or only individual triggers. And if we have multiple of them, we can have a fusion function of deciding based on the individual scores we get, making a decision whether to record or not. And now, in order to develop this whole framework, we are building a development framework, a data selection lab, and we explicitly have the perception function outside of this. So these could be, we regard those perception functions basically that come with their individual code repositories, machine learning architecture, the different training environments with all the software dependencies and their evaluation scripts. Regard them as our internal customers that have requirements towards data collection and want to use our plugin framework, also our trigger methods that we already developed, plus our benchmarking pipeline to bring in their requirements and triggers to enable data collection for the specific use cases. And then on the right side here, you see our in-vehicle Instinct module, the embedded runtime. That's usually in a different programming language. And here we have a native implementation of our triggers. It's hardware accelerated, it includes the model inference, and then the fusion and so on. So there are several challenges regarding this process. So first of all, in order to enable our internal customers, our function development teams, to use our universal framework, that we need an easy-to-use API, so to make it easy for them to develop new trigger methods, to pour in their data requirements and use them to benchmark the triggers, along with including this in the training process, and then being able to deploy to the car. So what we also want to do here is we do not force any team to use a specific software, right? We want to treat the perception stack as a black box in order to remain framework independent. And we achieve this by having letting the team decide on their own which framework they want to use, whether they use PyTorch or TensorFlow or whatever. We just require that the models are exported as a framework independent representation. In our case, we use ONNX. And then we can use that within the inference parts of our development framework. And also, then if we want to deploy it, of course, we have further optimization steps that we need to do for the specific hardware use case. For example, if you have an NVIDIA platform, you could use TensorRT, or if you have different target platforms, you can use different types here. So of course, the whole thing only makes sense if we have this integrated into the Cariad data platform and MLOps framework. So to hook it up to the right place where the data has to be recorded to, but also from where it can be deployed to the cars and so on. And then another challenge is this translation from our more Python-based back-end prototyping environment towards the in-vehicle C++ environment, which is an optimized environment for runtime, of course, and memory and so on. So what we could do here is we could, of course, develop the triggers right away in C++, but this will generate only slow insights because it's more cumbersome. Our data scientists like to do rapid prototyping with for example, Python and all those frameworks that are available. So what we need to do is to port this Python code to the C++ environment kind of manually, and that's very expensive, very costly also. A better way would be to make as much as possible use of the existing Python code and deploy it to the car directly, right? Where at least for the calculations or computations where this is still efficient. So this is why we look at inter-process communication also, where we look at different technologies, how we can bridge the gap between C++ and Python. And do not go into details here, but an important aspect here is the zero copy aspect. We don't want to, or we want to reduce the copy steps between the Python and C++ world. That's easy if you do it on a GPU with shared, on a CPU with shared memory. But it gets much more involved if you also want to enable this for the hardware accelerated parts like the GPUs, and this very much depends on which platform you are on and so on. So then we also have a challenge with respect to the integration process. So usually our data scientists can generate quick insights using this rapid prototyping. But before we can let any software go into the customer cars, we have to have really high code quality standards, right? So this translation is not so easy. So usually our data scientists might, I don't know, they're very quick in picking up new methods, new technologies from papers from recent conferences, and they find code on GitHub they can build upon and want to get this deployed to the fleet because it runs locally very efficient. But now, of course, it's a different story if you want to integrate this into the embedded parts of a customer car, because we need to have high quality standards like documentation, test coverage, but also the types of tests, integration units, regression, code quality, whatever. It also has to be runtime efficient on the target device, right? So it must be efficient to run there. And if you think about using code from GitHub, we of course have to have a proper open source license checks in place to make sure we're using the code in a compliant manner. So what's special about automotive also and safety critical applications is the requirements that we have must be linked to the code artifacts. So we always need a full traceability from the code that we deploy to the car, or the software artifacts we deploy to the car, all the way down back to the requirements where they originate from. So what are the data requirements? Why are we using this method for this specific data collection campaign? All of those aspects have to be traceable in our development process and pipelines. So then you see, and I hope I can convince you that this sounds like a simple data science thing here. But of course, in order to make this proper solution that ends up in the customer cars, there's really a lot of other competences needed. We need software engineering, we need cloud engineering, we need data engineering embedded. We have scientific computing aspects, right? The hardware accelerator stuff, and all the systems and requirements engineering. So we need all those competences to form a proper solution in the end. And with that, I want to motivate you to go on our webpage and look for for openings that might fit to your competences, and we very much like to get in touch here. So thank you for listening.
Hello, Nico. Welcome back to the live stage. Thank you very much for this interesting talk and those really awesome insights on data selections. I got some flashbacks to university where we played a bit with image recognition. Very funny stuff. So I would say, if you're ready, we can jump right into a Q&A section as we have some questions. Maybe quick reminder to all of you, we have an extra question function. Please don't write them in the chat, as maybe I will overlook them. So maybe first question, what cloud service do you use? AWS or GCP? And what framework, TensorFlow or PyTorch?
Yeah, that's a very interesting question, because we come from a very diverse environment. The Volkswagen Group is really huge, right? We have different brands, and in the past had different departments working on different parts of the whole story. And now we founded Cariad 1.5 years or two years almost ago to kind of come together to a unified working model and architecture. And now one big requirement for us is that we stay as much as possible independent of any framework, but also of any cloud provider. So all the infrastructure we try to create needs to be portable, but also the frameworks that we use are very much diverse. And depends on the team that uses them. And so we have PyTorch, we have TensorFlow, but as I said earlier, we really want to make sure that that's not our problem. If you think about data collection, the teams can use whatever they want. We need to agree on a representation that is independent of the framework, and then we can see how we deploy it using the tools for the specific hardware. Yeah.
Okay, thank you very much for the elaboration. Jacob asks, how does random trigger decide to select the data?
The random trigger, yeah, that's very easy, right? You can just basically throw a dice or flip a coin that is maybe biased, so you select how many images you need, or what portion of images you want to select from the overall stream, just using a specific probability, basically, and then use a random number generator to pick up only a specific portion of the data.
Okay, thank you. Okay, another question from Dragan wants to know, how comes the random triggers mean IOU distribution is that much better than the individual models? From slide 13.
So it's not that it's much better than the individual models. We did several trials because we also realized that it depends on several factors how the performance in the end will be. So we did this experiment multiple times, like 10 times, and then in each experiment you see a slightly different curve, and indeed there were cases where even the random trigger was in one case better than a specific trial using the uncertainty trigger. So there's also an overlap, right? And this is due to first of all the data we used here, the data set. It was not an open world data set, but rather a pre-prepared data set, but also this softmax-based uncertainty estimation is really only the most, as I said earlier, or I like to call it the most naive way to think about uncertainty estimation. So of course you can, looking at the softmax, we know that models often are overconfident with respect to their own softmax scores, and that you can have different measures in improving this by, for example, doing calibration of the softmax scores, or you use other uncertainty methods like the Monte Carlo dropout I mentioned earlier that might be better and select even better data. So here we just showed that on average, our uncertainty or softmax-based uncertainty measure is better than random triggering.
Okay, thanks for that answer. Chiri Harasim at Databricks, sorry for butchering that name, wants to know, how do you avoid regression of models? How do you monitor models? 2 questions packed in one. Smart.
So, I mean, how to monitor models is actually very, very interesting. I hinted at this research project we do with a lot of partners from academia and industry, where we look at how to really make models safe, right? Because that's why you want to monitor it, right? In applications. So there are a lot of metrics you can apply, and these are basically also related to what we do here for what you use for data collection. Methods that estimate the current uncertainty, estimate the fluctuation over time, or other aspects, or stability if you use, for example, perturbations in your predictions. And all of this can be done on the side. Of course, it needs some more compute we have to reserve for this in the production car. But those can be metrics that run on the side, monitoring our currently running models and analyzing and getting estimates on whether the model is really doing its job well, or whether there are situations where we cannot trust the model so well, so that we can that we have to act otherwise and have other measures in place, alternatives.
Okay, thanks for that answer as well. David wants to know, do you use NLP also?
NLP, like what NLP, natural language processing, or what do you mean? Or ML?
I'm not sure. Maybe, David, you can write it in the chat. I will take another question in the meantime. Martin, a very basic question. Martin wants to know, how did you start with machine learning? Are there any tips or tricks for beginners?
Oh, yeah. I mean, there are really a lot of resources available in the internet regarding machine learning. Of course, you have also some courses you can take in different platforms where you can really have qualified machine learning courses. But there are also a lot of resources if you just in tutorials, if you just go in the internet and search for it, there's a lot of material. Also, many universities started a few years back already to publish their recordings of their lectures and put them online, and that's very helpful actually for learning it.
Okay, thank you for that insight. Another question from Fabian. How is your life now compared to your PhD in Zurich? How much % can you use on machine learning and how much on meetings?
Yeah, that's a good question. Of course, in the more senior you get, of course, the level of actual doing coding might reduce with respect to compared to the meeting overhead. But yeah, I'm still, I guess, in a position where I can use a lot of my experience to also guide more junior people on this. So I think this also, yeah, it's a development.
Okay. David now wrote, yes, it's natural language processing. So do you use natural language processing also?
Yeah, so personally, I focus more on autonomous driving tasks, where we usually have like perception as the biggest problem, environmental perception. But of course, we also have teams that deal with natural language processing in the context of infotainment and personal assistant and things like that. So if you think about our navigational systems, they work with speech recognition and so on. So we also have technologies to be developed there, and definitely it's an active field in our development.
Okay, thank you. Philip wants to know, what do you look for when interviewing data scientists?
Okay, so I think Many things. So of course, the personal aspects, team fit aspects. But if you think about competencies, there should be a solid background on machine learning, right? And how to use the existing, and also on coding, how to use the existing technologies in a structured way also. I mean, when coming from research, especially as myself, I have a background in university, and then in group research of the Volkswagen Group. It's not so critical to develop high quality code, but now the closer we get to the serious production and build technologies and code for that, we have a lot of code quality standards we need to fulfill, and for this we need software engineering competences as well, and things like that.
Okay. Yeah, Philip, sounds like you're looking for a job at data scientist. So just go to WeAreDevelopers.com. Maybe the perfect one is waiting for you there. Next question, maybe. Yes, Perry wants to know, I'm interested on security side. How did you handle security issues in your daily platform operation?
Yeah, good question. I'm not a security person, so I don't know much about what our IT teams do for security. We have a division that is dealing with that, and that is looking into all our systems, actually, be it the local development clients, be it the cloud infrastructure or on-premise data center infrastructure. So there's enough room, let's say, for security issues, and also for, if you think about the customer cars, of course, the platforms running there need to be secured. So I cannot go into details because that's not my area, but I can tell you we have divisions specifically dealing with those topics, and you will probably see openings also on our webpage.
Okay, thanks for that. David has another question. Are Kaggle competitions good for start in AI?
Yes, definitely. I think that's a good way to practice your skills and to also get in touch with other developers, right? So the best way to learn is exchange with other people. So usually you can form teams, or you can have chats about in different fora to discuss about the approaches you used or tried, and I think it's a very good way to go forward with this topic.
Okay, thanks for that answer as well. Pascal wants to know, what do you think about implementing AML and MCU for some automated task predictions?
Okay, now AML, I guess you mean AutoML. MCU, I'm not so sure about.
Yes, he means AutoML. Sorry for that. He corrected.
Okay, so in general, everything which we can automate will help us in the end. However, we always, of course, have to look at the costs of this because AutoML can get costly, right? I mean, if we really think about using architecture search for finding a good way, then in an automated way, it can become very costly, because every single trial, single training is taking, I don't know, maybe days or whatever, depending on your function. But that also depends very much on the use case. So I mean, if I think about vision, that's a heavy task, but we also have products that only need kind of very small models, and there you can leverage this AutoML approach more, right? You can try more different things because the individual costs for each trial are smaller, and so it makes sense to use them there specifically. So microcontroller units, you mean? Okay, so that's actually very interesting, because it's also one topic we have in our research project, KI Delta Learning, actually, where we look at not we as Cariad, but the partner of us looking at how to include the neural architecture search in the a hill setup, so in the hardware in the loop setup. So having the microcontroller unit or the target hardware included in the loop of doing this search. And that's, I think, a very useful thing, because you have many more things to tweak that are specific for this hardware, and that makes a lot of sense. But as I said, similar needs to kind of weight up the costs for that.
Okay, thanks for that as well. And maybe from Liang Yu, another question. When using uncertainty, how would you distinguish valuable data points from outliers?
Yeah, that's, I think, difficult. So usually uncertain samples are ones that are close to the decision boundaries, right? To any decision boundary. Outliers can be, I mean, it really depends, but they can be in a region of our decision space that is clearly lying very far away from this decision boundary. So we have a clear decision. However, it might be wrong. And so our uncertainty detector might not detect this case. For this, we would need different technologies. And that's why we developed this plugin framework where we can have different triggers running side by side. And we could have one that looks at uncertainty, but we could have another one that really takes, for example, diversity or anomaly into account, looking at how far away is the sample in our input space. And this might be better suited to detect those outliers. So it might be a combination of different approaches in the end.
Okay. Nico, thank you very much for coming. Thank you very much for the interesting talk and your very detailed answers. And many greetings to Berlin. Hope to see you again in another topic day.
Thank you very much for having me. Have a good day.
Thank you. Bye. Thank you. You too. So, and before we start with our second speaker, we'll have a short break of about 4 minutes. See you then. Hello everyone, back again at the WeAreDevelopers Machine Learning Day. So after this first very interesting talk, we have a second speaker already waiting. He is a tech lead at Aizonic, has also an academic background in artificial intelligence and informatics as well. And in his spare time, he teaches programming courses and he likes to speak at conferences such as ours. Please welcome with me, Bas.
Hello, everybody.
Hello, Bas. Wonderful to have you. How are you?
Thank you. I'm very well. How are you, Benedict?
I'm very, very well as well. Thank you. Would you mind telling us where you're calling us from today?
I'm calling from my home, as I think a lot of people are, and I'm based in Utrecht. That's a city in the center of the Netherlands.
In Utrecht. Oh, I see. So, Bas, please tell us something about what we're going to learn from you today.
Yeah, the subject is MLOps, so how to run machine learning models in production. Previous speaker Nico already mentioned some of the work that he has done on that, and what I see is that a lot of companies are struggling a bit with this because it's a relatively new subject. Machine learning is of course not so new yet anymore, but running it at scale in an enterprise that's quite a challenge for a lot of companies. So I'll talk a bit about that, and I'll talk a bit about the technology and the architecture, of course, how to do that, and I have some examples of that. But I will also mention a lot about how to build your team and what kind of cultural aspects are involved in this.
Bas, that sounds so interesting. I'm hyped, I'm ready, and I would say the stage is yours.
Thank you very much. Okay, let's start with my slides. They're here already, I see. So thanks for joining this session, first of all. So what I mentioned already, I will talk a bit about MLOps in the next couple of minutes. A bit about myself first. Benedict also already mentioned that I have my own background is in AI, so I was a data scientist, you could call that, but that was still in the old age where we didn't have these many fancy frameworks yet, and these out of the box models. So we had to do a lot of programming ourselves to get a machine learning model or a neural network somewhere in production working. And since then, I've been focusing more on data engineering and architecture. Currently, I'm employed as an independent consultant. I have my own company called Aizonic. And I work at a company called Wayfair, which is an American home goods website, very, very large retail website. And I will also give some examples of that in a few minutes. You can find me on Twitter, LinkedIn, etc. Would be happy to connect. So please reach out. And what I also do sometimes is speak at conferences and also do a bit of writing. So these are two titles that I recently wrote or co-authored, I have to say, because I was not the only author here. I wrote a bit about MLOps in a packed hands-on book called the Artificial Intelligence Workshop, and I also wrote one of the 97 things every data engineer should know, that was published by O'Reilly recently. Right, let's go on to the topic, machine learning in production. It starts, of course, with machine learning. This is the machine learning day, so I not give too much of an introduction, but I think machine learning is a complicated subject, right? So if you're a data scientist and you learn how to build models, you will end up with these kind of diagrams. Machine learning is divided in all kinds of categories, all kinds of different sort of algorithms, all kinds of different learning methods, and all kinds of different technologies. So there's a lot to learn and a lot to comprehend, and it's a very broad subject. But how do people normally do this? They do notebook development. So typically a data scientist, when he goes to university or he goes to a course online or wherever he learns it, almost the first piece, the way that this subject is being taught is by doing some kind of development in notebooks. And notebooks are great. They are great technology. They are very easy to use because you can just you have immediate feedback of your code. You can write small pieces of code, run a cell in a notebook, for example, and get immediate feedback from those results. And those will still be visible for a while. So it's a great way to, for example, experiment with data and to make some small changes and then reflect back on what's happened and maybe visualize things, etc. there. And this whole notebook development with tools like Jupyter Lab, were actually adopted by the data science community because they are so easy to use. But that doesn't mean that they are good to work in a production environment, because notebooks were not intended to work in that way. They were intended to give you this fast visual feedback and to visualize data and code and results of your algorithms. But they were not intended to use in a production setting. They were more for experimentation and maybe some of the development tasks that are out there. So this is not yet machine learning in production. Of course, this is only the start of your whole journey for bringing this to production. And in a famous paper that was authored by some people at Google already in 2015, this was already recognized. Because what you see here is that this really small black box here in the center of this diagram, that is the machine learning code that you might develop in a notebook. But there's a lot of tools, technology, mechanisms, processes, configuration, management, governance, you name it, around that. Because your very fancy, complicated notebook with your machine learning model that has been trained and that you spent probably ages on building and a lot of research on to get it right, is still only a very small a small gear in the big gearbox of running software in production. So that's what we're going to talk about. We're not going to talk about a black box. We're going to talk about all of the things that surround it. And what I want to start with is because MLOps is mostly not about technology or tools or frameworks or even architecture. And I will definitely come to that. What I want to start with is more the mindset and the culture that you should employ. It's not called MLOps for nothing. It's a bit of a continuation of DevOps. So as a reminder, DevOps was released or was invented probably something like 10 years ago. I don't remember the exact days, but I do remember when I was at companies that were going to use DevOps as their way to develop software. Because before that, it was very common for companies to have a development organization and an operations organization, and there was a big wall between them. And once developers had created something, like a piece of software they want to use in production, they would throw it over the wall to the operations guys, and they were responsible for maintaining it. That was the old way of developing software, and of course that was still the waterfall method was also very popular. Around 10 years ago, there was a big change in that kind of thinking. Said, okay, that's not so good. It's not efficient. We should actually combine developers and operational people in one team. They will still have their own specialty. Developers will probably write most of the code, and the operations people will probably do the most of the configuration management in the infrastructure, for example. But they will be in one team, and they will have one single shared responsibility to develop and maintain software in production. And that was a big shift in this kind of thinking, where things were much more integrated and made more efficient. And and I really saw it, because at that time I was working for a company like ING Bank, a big bank in the Netherlands, that really transformed the way that software was developed. And things were going much smoother, much faster. And it was also much more fun to work in that company, because there was no more, difficult handovers and long development trajectories. So it was all about the teams and about this mindset of developing things together. And MLOps is the same, but then with maybe a bit of extension, because what we add to the bunch is machine learning. And similar to the previous situation where we had developers and operational people, we now add a new specialty, and that is the data scientists. So people who are in a machine learning team, what I saw happening in a lot of companies was that they were also a bit separate from the rest. They will have their own, like maybe research department or their own small group of people that were doing data science, but there was not really an integration with the other parts of the company because there was no integration in the teams. But that is, of course, what we want to achieve. We want to achieve the same way as the DevOps revolution. We want to have the machine learning engineers close to developers and the operational people so that they work combined on a single responsibility, namely one application in production that happens to have a machine learning model somewhere inside it as a part of their business goal. And the goal of that is, again, similar to DevOps, to gain trust and speed. So if you really apply these principles in the correct way, then things will be easier. With continuous integration and delivery, you will actually gain trust in developing new models and putting them into production because you've done it lots of time before and it all went well. Continuous monitoring, so there will be there's not a model that is from an obscure source that you have to deploy once. No, it's a continuous effort of improving the model, checking what the results of the model are in production, adjusting it, logging it, etc., and that's a team effort. And by that way, the speed will increase in developing these kind of applications. Now, the roles and responsibilities in those teams will be a bit different than when if you would have a team without any machine learning algorithms inside their responsibilities, because of course you will add something to the bunch, which is machine learning. And I already mentioned that this will be typically be done by a data scientist. There's also some other roles that are currently arising, like the machine learning engineer, which is another specialty for basically productionizing these models, for integrating these machine learning models into the infrastructure of the organization, serving the models in that sense. And also the data engineer, a role that we already had before, to prepare the data and to for example, acquire the data from source systems, make it available as features for the machine learning models that the data scientists are training a model on, and also make those data available as features in the real life production environment. Well, these roles can be, of course, shared. So it doesn't mean that you have 4 or 5 different people in one team. You can have a team easily with 2 or 3 people, where, for example, one of them has a combined role of, let's say, data engineer and machine learning engineer, or maybe of a data scientist and data engineer. And this is more that you should be aware of this kind of work that needs to be done when you're actually moving to a MLOps team, and when you actually add machine learning to your team responsibilities. Maybe also good to mention again the Spotify model. This is a very popular team structure model that I've seen in many companies already, which is really handy to use. Although Spotify is not actually using it themselves, I was told. Actually, this is from an article called "Spotify Doesn't Use the Spotify Model." But anyway, it's successful for a lot of teams, and that's what matters. So where you can actually structure your organization in tribes and squads and chapters, so that even though you have teams with a single responsibility where all these roles are combined, data engineers, machine learning engineers, data scientists, dev engineers, etc., they will also be organized in chapters so that they have still a common home to discuss their own subjects and to discuss their own expertise, because still, of course, a data scientist will have different interests and different technologies to work with, etc., than an ops engineer, for example. Some best practices to put the machine learning models in production that I do want to mention here. Maybe some of them are already familiar with you, but maybe good to mention them as well, because this should be clear in the team. Like, how are you going to do this? How are you going to to structure your model in production. First of all, these models are just artifacts. So they can be versioned, they can be provided with certain metadata, they can be stored somewhere. It's not like this is a very special breed of obscure code or so, which is somewhere in a notebook. If you have that situation still where there is machine learning done, which is running somewhere in a notebook that gives some predictions, then you should really think about the next step. Okay, that's maybe your development environment, your notebook, but your actual model, we should treat it as a proper artifact, like we have other things, like we have other source code, like we have maybe images in a web shop, like we have data in a database. That is, and you want to do proper governance and maintenance on that, and add metadata, etc. to that. What you also should realize is that machine learning models change over time with the data. So when you're putting a machine learning model in production, you should definitely continue to monitor it and to test it on a regular basis, and actually update it, for example, every week or so, because the behavior of the data that your model uses, let's say it's customer data, for example, will change because the environment changes, because people will get different opinions. So the pure characteristic of a machine learning model is that it's trained on data, but it's not finished. It needs to be retrained every time, and for that you need to be monitoring it, testing it, retraining it, and also checking if your model is not diverted too much from your data that's already still trained on, and that we call that data drift. And one other recommendation I would say is not only to look at the if you do a monitoring, not only look at the technical aspects, like how fast is your model responding, how many times is it actually called, what is the CPU load of my server that runs it, or something like that, but also look at the business metrics of your model, like how accurate is your model actually still running in production? Because even if you keep on retraining your model, it can be that your model is actually losing accuracy because the algorithm that you used to train your model on is not as accurate anymore based on new data. So you probably would have to redesign your model, maybe using a different algorithm or use different hyperparameters for your model, tune it a bit. And that's of course all to optimize and keep the model accurate. Right. Let's move on a bit to the bit more technical bits, the architecture of machine learning, of MLOps. And if you Google this, if you search for, okay, how do I do MLOps? What is the tooling that I need? You will get a lot of very detailed, usually pictures that are usually heavily biased towards one or two vendors or technologies, etc. So what I really wanted to do is get an overview, like reference picture in place that kind of captures everything and captures the big idea of MLOps. And this is what I came up with. It's very simple, and that is on purpose. So there's also a bit of things missing, but this captures the essence, I think. To put a machine learning model in production, you basically need two pipelines, two pieces of your architecture: real time and batch. The batch part on the bottom half of this diagram is actually where you train the model, and that's pretty much always done in batches. Because even if you apply something fancy called online learning, then your online learning mechanism will still be a batch job that runs maybe every minute or so, or every hour, and which is like almost real time, but it's a batch process. But normally what people will do in a company is they will capture data in a feature store, keep it there for, let's say, a few months or so, and then run a model retraining pipeline that trains the model every week, for example. And with that, an artifact comes out of that, which is your machine learning model, which is exported to a temporary file and stored it in the model registry. And that is just a batch pipeline that is scheduled, for example, to run every week. Once that model is then there available for you in the model registry, it can be, of course, used in real time in a scoring pipeline. And that is, of course, so as an example that I would like to use is the web shop of let's say a big retail company like Wayfair. We have many machine learning models in production. They all follow this pattern. They are retrained on data that we capture about our customers, about our products, about our suppliers, about our carriers, etc., continuously. Then once a model needs to be retrained, it creates a training data set out of that data coming from the feature store, and it executes a training algorithm that runs for, let's say, a few minutes or maybe a few hours, and produces a model artifact in the model registry. Next to that, there's of course the real-time pipeline that is using these models, serving the models, scoring the models in production, and just picking those models up from the model registry. And that usually involves also some data preparation and some post-processing, because the models themselves will give a bit of an obscure output, like a score. Maybe there's a score from 0 to 1. So what is the likelihood that a customer will also order a sales item? Yeah, that likelihood is 0.7. Okay, what does that mean? Do we have to show them an advert? Yes or no? That's post-processing, for example. So that's not only the model itself will not give you that actual action, that actual message on the website or an alert or whatever you want to do with that. It needs to be post-processed. So if you have this picture in mind, then all of the other architectures that you can find online will follow this pattern. And I can really guarantee that is the case. So for example, in Google Cloud, if you look at how Google is doing MLOps, you get this picture. If you do a deep dive in this, you will actually see that it's exactly the same pattern. There's a batch job that is doing the model training and producing a model artifact to a model registry. And of course, this is biased or branded towards the Google infrastructure, because Google would not say use a different technology for it. They will say, we have a dedicated tool for this to store your model in the model registry over here. But it's still the same pattern. Once the model is there, it will be picked up from a real-time model serving component and used in prediction services. Same for Azure, and we'll do a deep dive after my session, because the next presenter will go into details about this. This is the Python machine learning environment for Azure. Same kind of pattern, but different technology and different tooling that you can apply for this. And Amazon AWS, same. They have this whole SageMaker environment, but also follows the same pattern of the batch and real-time pipelines that you have there. One concrete example is how we do this at Wayfair. We have a batch pipeline here that runs in Vertex AI, where actually the features that we have are stored in BigQuery. So we run on the Google Cloud. So the features that we store are being collected in BigQuery and Vertex AI feature store, and they run periodically as a Vertex AI model trainer. That's the batch job that produces the model. And the model is stored in the model repository that we call it, which is a custom-made tool at Wayfair. And that's been then being served in an API that runs on Kubernetes. So again, following the same pattern, but with a bit of mixture of, cloud-native tools from Google and some homegrown, custom-made tooling here. So I want to do a bit of a deep dive into the tooling itself, because this is also very interesting for a lot of people. And if you look at MLOps tooling, you get something very complicated like this. This is coming from the Artificial Intelligence Infrastructure Group, I believe. What can be seen from these kind of pictures is that it's a dynamic landscape. So there's lots of tooling for lots of very small specific pieces of your puzzle, not only model serving and scoring and training, which is the most common ones, but also, for example, data quality, model observability, for example, all kinds of integrations with other tooling, with data warehouses. But there is a lot of tooling available. That's for sure, and you just have to, you have to make your pick out of that. And I cannot really recommend some of the tools to you or to any company if I don't know, of course, the company, because that is what really matters. What fits your own environment? What fits your own culture? What fits your own team? You can go many directions, and there's a few discussions that you should be following. First, buy versus build. Maybe the very traditional discussion that you will have in many cases, in many companies. What are you going to do? Are you going to go with a vendor, which you will pay a license for, and they will provide you a tool that does what you need, hopefully, or does everything, and then you only use a small part of that, etc. Or are you going to build your own tooling that does exactly what you want, and it's a customized tool, but of course you have to maintain it yourself, so that comes with a certain effort. And the other discussion is, okay, are we going to go with AutoML, or are we going to go with more a custom approach again with the models? Because there's a whole revolution going on in machine learning now, all aimed towards AutoML. If you hear the big companies like Amazon and Microsoft, they will focus a lot on AutoML, but they also do that to drag you into their ecosystem, of course, because then you're hooked into their products, which is not a bad thing per se, because if that makes it very easy for you to build your models by, for example, just throwing some data at it and clicking a few buttons, and then voila, you have a trained model with an endpoint, that you can actually automatically call. That's a great effort. Some companies will also choose to say, okay, now that's great, but it doesn't work for me because it's just not customizable enough, and we need to have more control over the models, the algorithms, the data, etc. So maybe that is a better fit for your organization. So these are the most important choices that you have to make before you actually going to select one of those tools, or maybe one of the big frameworks, because there's also integrated tool sets like Databricks and H2O.ai that do it all for you. You should first make these decisions: buy versus build, and AutoML versus custom built models. That being said, I do want to go into a bit of deep dive and some examples for the tooling, starting with model serving, because that's a very important subject, of course, when it comes to building machine learning model applications. And also I want to start with the realization that there's multiple ways to do this. Also, there's multiple tools to do this, so there's also and frameworks, etc. for this. But first, you should realize that there's multiple ways to serve your model, so to make it available for example, a website to use it. Starting from a more integrated, maybe monolithic approach. On the top here, you see that what you could do is deploy your model, your machine learning model, which is an artifact again. It's not a notebook. It's an exported file. You could deploy that together with your application. So you would have an application, and if you press the button in your continuous delivery pipeline, your one single application gets deployed to production, including your machine learning model, and maybe also including some business logic, an API, maybe even a front end, but usually that is decoupled in an app or in a website. That's certainly an option, but it's a bit a monolithic approach. And what I always said, probably your model will be updated with a different frequency than the other parts of your application, because your model needs to be retrained. It needs to be retrained maybe every week or every day, and then your this model needs to be published in a new version of your application. And that's not really a common way to do it. Much better practice is to decouple it. So to say, okay, I recognize that my model is integrated, is connected to my API, to the business logic of my application, but it's not actually a part of the same model repository or code repository, and also not the same CI/CD pipeline. It's a separate process and a separate entity and a separate application component, more a microservice. If you recognize that, then there's also several ways to structure that. For example, you could say, let's host my models in a dedicated application, because there's tools available again that you can buy that do exactly that. They will say, okay, we will host multiple models of you, multiple versions of each model, multiple models next to each other, and this tool is just doing that. It's serving your models to be used by other parts of your application. And that's a good approach, because then you have it decoupled. You can release, update, retrain your models independently of the rest of your application. Of course, you have to keep in mind that if the interface changes, then both parts of the application will change. But usually only a retrained model is just a new version of the algorithm below the interface, not the interface itself. So that is a common approach that can be worked perfectly in an enterprise. Another decoupled approach is to API-ify your model and basically have it even more decoupled and say, okay, I just see my model with a thin layer on top of that as a microservice. And if I want to have a new version of that, I redeploy my model plus my small API layer on top of my model, and I can just still call it from the same interface and from the same URL, etc. Or gRPC location that I had previously, only my model has been retrained. So it's even more decoupled, and each model will have their own microservice available for them. Also a very common approach. One specific or one special case is when you want to use your models in a streaming context. So if you are doing data streaming, and you really want to evaluate your models in near real time, and I'm talking about really with a requirement of latency of, let's say, 10 milliseconds or maybe even less. And we have those use cases, for example, in companies like Wayfair, but I've also seen that at banks when you do, for example, fraud detection or something. You really want to have split-second model evaluation in production. Then actually a structure like this, where you have a tool that serves your model, or a microservice, or some place on the network that serves your model, might just not be fast enough, because there's some latency, because maybe there's too much time needed to serialize, deserialize your API request or something like that. There can be reasons why this is just not fast enough. And actually, a very common approach in stream processing applications is to just serve your model together with the rest of your streaming code as part of your data stream processing engine. And that looks a bit strange, because it looks a bit, again, as the monolithic approach that I said in the first place. Don't do that, because it's too much things together. But in streaming, it is kind of a good pattern again, because you just need it sometimes to get the performance that you need. It does mean that there are some mechanisms available that you can actually use to lazily load your models in memory in your stream. So that's what you do. You push your models as an artifact and load them in memory in your stream, and still keep your stream running while you're actually doing that. There's frameworks again available for that, and also intermediate formats for your models like PMML and Onyx that can export your models to an intermediate format and have them lazily loaded in memory. So once you refresh a file store or a database where that model is, it lazily gets loaded into your stream without interrupting the stream processing engine itself. Maybe a no-brainer, but I would really recommend, if you are developing this kind of software, to put everything in containers. maybe a bit of a strange concept again for data scientists, but nowadays I would really recommend to go with Docker and Kubernetes as your de facto application release mechanism, because this will really improve the way that you can test, scale, and basically work with all of your software, independently of how you do this. If you want to have your model API-ified, and you would have like a single microservice to run your model, or if you want to do more with shared tooling, etc. It's really good practice to actually containerize all your code, containerize all your methods, make them available, as containers, as Docker images that you can run basically from any infrastructure. Also, I really like this concept of being a bit independent of infrastructure, whether it is on cloud or premise or maybe even your own laptop. Everything will just be running as in the same context if you are properly Dockerizing your code in that sense. So that's really important, also with machine learning models. Then I already mentioned the concept of a feature store, something relatively new that arose maybe 1 or 2 years ago as a specialistic database, because that's in fact what it is. A feature store is actually a database for storing features. And it is specialized for being able to serve those features in both real time and batch. So what you usually see if you have a real feature store, because there's also some feature stores that are not feature stores, but they are more feature definition stores. So they are pointing to other locations where the features are actually stored. But if you have a real feature store, then what it would be really good at is having an API where you can query your features if you're doing a batch job. So if you want to say, okay, I want to have all of the features to train my machine learning model on, and they will also provide an API to get one feature, for example, for one customer in real time, because that's what you need when you are scoring the model. And that is a bit difficult to achieve with a common database, because there's normally a trade-off between, for example, performance and the amount of data that you can store. Or there's a trade-off between how fast you can ingest data versus how fast you can get data out. And a lot of feature stores that I saw actually solve this by having two databases. One is for a NoSQL database that has extreme high performance, which serves the latest features in real time, and one is a database that is used for getting big data file sets out if you're doing model retraining, for example. So nowadays, it's not a must-have or so of a feature store, but it's really a record if you're doing machine learning development on large scale, and you really want to collect your features and aggregate them and make them available for both your machine learning models retraining and in real time if you're doing feature scoring. Then a feature store is really a recommended technology to have. And luckily, it's also becoming much more mature. Like 1 year ago, it was still a bit difficult to get a proper feature store running in production. But nowadays, all the big vendors have one, and you can actually choose which one you like. And finally, another very important thing to spend some time on is workflow orchestration, because we have batch jobs in a machine learning environment. We have batch jobs to train the model, maybe also to score the model. If it's not being done in real time, we will have probably batch jobs to do feature engineering, to calculate your aggregated features, for example, to take averages for a certain value that you want to store as a feature. And all these batch jobs need to be orchestrated. They need to be properly maintained somewhere, so you can schedule them. You can visually see what is the outcome of this batch job. And if you would do this, maybe in a bit of a crude way, maybe with just a cron job, for example, or maybe some kind of low-level framework, then you'll probably run into problems when you want to debug things or check the results or other kinds of maintenance efforts. So I would actually really recommend you to invest in a proper workflow orchestration to manage everything like this. Some examples that I put here are Kubeflow and Airflow. I both have good results with those. But again, I also know that there's dedicated tools. For example, there's Azure Data Factory. There's also dedicated tools on Amazon that you could use, or maybe you have your own preference. Whatever you pick, make sure that you properly maintain it and also treat those workflows, treat those batch jobs as proper artifacts again, and version them and schedule them and develop them as you would have normal artifacts of your application, like your source code. All right, I would like to wrap up because we're almost out of time as well. I talked about a lot of things. First, starting a bit about the culture, really, hopefully giving you the realization that notebooks are just the start of your machine learning setup in production. And I talked a bit about the architecture pattern for MLOps and the tooling for that. And if you want to know more, then there is plenty of things that you can look out for. First of all, of course, maybe the book that I co-authored. There's also a nice Coursera specialization now on MLOps, which might be interesting for you. Also, there's dedicated courses in sites like Pluralsight, etc., for specific technology like Google or Azure, if you want to find that out. And there's some websites like the MLOps.org organization and the Artificial Infrastructure Alliance organization that I already mentioned, that provide great resources for working with MLOps. And that was it. I would like to thank you for your attention, and I think I will switch back to Benedict and see if there's any questions. I think you're on mute.
Oh yeah, sorry, I was muted. Totally my fault, not. So welcome back on Live Stage, Bas. Thank you very much for this interesting talk. I hope you had fun presenting it. At least it looked like it. Yes. Are you ready for some questions?
Yeah, definitely. Yeah.
Definitely. Awesome. David wants to know, what do you think about Coursera MLOps specialization by Andre Ng and Lawrence Moroney?
It's great. I just recommended it in my previous slide, I think. So it's
you did.
It's a good course, yes. Because what's nice about that course actually is it's a bit vendor neutral, which I think is a good way. Of course, if you work in a company that is already invested in a certain technology, you should probably also learn that. But in general, I would recommend also to learn a bit about the general concept of this. And the MLOps course tries to do that, pretty well.
So, big recommendation from you. Another question might be, how did you get into machine learning, and are there any tips for beginners?
Yeah, so well, my own background is I went to university and I studied artificial intelligence, so that's how I got into machine learning. But then a lot of years it was not really a common practice in big organizations. So it was very academic. Nowadays, if you want to start with machine learning, there's few things that you can approach for this. I would definitely try some of the great courses online that are available. Again, in Coursera, for example, there's great MLOps courses. The great machine learning courses for that. But also, I would really recommend to keep your developer background in mind, so to say, because what I also see is that the quality of data science work that is out there is because people have only learned to work on the algorithms, and forgot about the common best practices and coding guidelines and all those kind of things that you would normally learn when you are doing professional software development. So that leads to messy code and not good integration, no good governance, no tests, etc. So I really think it should be a combined effort of those two disciplines. Yes, you should learn the algorithms, and there's courses for that, but also keep in mind, how to develop proper, high-quality software.
So stick to your roots as a developer, and you'll do fine with the right passion.
Yeah.
So maybe another personal question. Do you remember your first computer or the first machine you've worked on?
Oh, yes. It was an ZX Spectrum.
Okay. No, I have no idea.
It's probably back in the 90s. Let me think, because I was around 8 or 9 years old, and we had a computer without any physical hard drive. So that was actually before the Commodore 64, where there was at least a cassette player that could store some of your memory. So there was a computer that you just had to program every time you want to use it. So
sounds fun.
Yeah.
So you became a developer out of need to use your computer.
Exactly. I still remember typing in basic listings. So 10 go to blah blah blah, etc. And then if you did it in the right way, you typed in like 100 lines of code. You had a small game like Pong or something like that.
We are so spoiled nowadays with our modern computers. But hard times create hard men or hard developers.
Yeah.
So, okay, you shared at the end of your presentation, you shared some further material, but is there anything other you might want to add, like books, blogs, YouTubers to learn?
Yeah, I could recommend some, but it depends very much on what you would like to learn. If you are a book person, let me give you one book that I would really recommend. This book from O'Reilly, Designing Data-Intensive Applications. If you want to start with these kind of concepts, or in MLOps or data engineering, that's a really good resource. But then, it's a bit maybe technical book, and maybe you don't want to wrestle your way to a very, very thick book. So you might actually just start with a small Udemy course or something like that. So that's also fine. So, yeah.
Okay, thank you for that. We just got another question from an anonymous user. Would you currently recommend freelancing in this area?
Yeah, I am a freelancer, so I would recommend it, but I would recommend it if you are confident with your own situation, so to say. So I would not recommend starting as a freelancer as a beginner, because then you will end up maybe in roles that are difficult to fulfill, and so. If you are more a junior, what I would recommend starting at either a consultancy organization where you have lots of support and lots of guidance for your career and for getting good projects and working at interesting clients, etc. Or maybe joining an organization like Wayfair as a more junior engineer, where you actually basically have the same support in the environment. As a freelancer, I would recommend to do that if you're a bit more experienced.
Okay, Bas, thank you for this very interesting talk. I hope you had as much fun as I did. And best greetings over there to Utrecht. Bye.
Thank you. See you. Bye-bye.
So, and before we will get to our final speaker of the day, we will jump into a short break of about 10 minutes. Stay tuned.
Have you found your dream job as a developer? Or are you stuck in an unfulfilling job? On WeAreDevelopers.com, you find over 1,000 jobs in Europe that fit the tech stack that you want to work with, and salaries go up to $130K. All you have to do is create a free profile, and you automatically get matched with jobs that fit your requirements. So what are you waiting for? Create your free profile and let companies apply to you now.
Hello everyone and welcome back to the WeAreDevelopers Machine Learning Day. So we had two awesome speakers already, but one to go. He is a software architect and developer community lead at Swiss Life. He also organizes the .NET user group in Zurich and although he's primarily a .NET engineer, he has also a passion for UI UX design. Last but surely not least, welcome, Jose.
Hi, Benedict. Thank you so much. That was an
Hi,
awesome
Jose.
introduction.
Glad you liked it. How are you doing, Jose?
I'm doing good. It's a sunny day here in Switzerland. It's really cool. Just can't wait to try to get out.
Perfect. It's also sunny in Vienna here.
Nice.
So, would you mind telling us what your talk is going to be about?
Yes, of course. I'm going to talk about how to get into Azure Machine Learning, or how to use it. Azure Machine Learning is a new, well, not so new. So it's been since 2015, 2016. We call it the Azure Machine Learning Studio Classic, right? Now it's deprecated. So it started like a drag and drop, easy to use, Microsoft style, that anybody can do machine learning. It was awesome. That's how I got into machine learning. Then I did some other courses. And I will show so target of this talk is developers that want to jump into machine learning and machine learning enthusiasts that would like to do machine learning in an amazingly easy way. And that is the promise of Azure Machine Learning. And that's what I'm going to show. I will show how to get into that, how does it work, and what it can do, which is basically everything a data scientist does. And then how it can leverage and how can you train models using the 3 different flavors of Azure Machine Learning.
Okay, Jose, that sounds very interesting and very promising. And I would say, without further ado, the stage is yours.
Thank you. All right. Hello, everybody, and good morning if you are in Europe. Otherwise, happy evening or night. And thanks for being here and listening to me. Into this world, it's hard to find a hottest work than data science, machine learning. It's a fast-growing field that's reshaping the world we live in and adding this strange and hard-to-find feature called intelligence in all the kind of devices, in your watch, in your mobile, in your computer, in almost everywhere. And it's changing the world we live in. It's incredible, hopefully for good, like self-driving cars, cancer detection, earthquake prediction, drug generation. And it's vast and powerful field that's defining the way humankind lives in. And also it will help you to open doors, to improve your career, create opportunities, and the way you work and live. As a fast-moving field, it's really has a catch, of course, and we need to talk about that. Coming back to what I was telling Benedict, in 2015, I got a new computer to do machine learning, to play with the Azure Machine Learning Studio. That's the computer I got. And this is what you see in the center is the Azure Machine Learning Studio. That's why you got a 34-inch monitor. That was the perfect excuse to be said. Here is some documentation, and that on the right is my cat, Whitey. That said, I had a big of a problem. I got a 1080 graphic card, Founders Edition from NVIDIA, which was amazing for doing machine learning and training what we call deep learning algorithms in there. But it took me 2 to 3 weeks to configure it, find the right drivers, configure the software that I was using. So it was quite cumbersome. And during that time, you are not learning, and you need to learn if you do machine learning, like almost constantly. It's a expensive job, not in money, but in time. So the promise of Azure Machine Learning is that all this training and configuration is done for you. You have at your fingertips ready-made machine learning computers that you can use, even clusters. We will see how to use them today. But first, as we said, my name is Jose Luis Latorre. My Twitter ID is GOSLET, which are the 3 letters of my name and my last name put together. The same for GitHub. You can find some of my code. And I work as software architect and dev community lead at Swiss Life, which I'm pretty happy. I have an awesome team. I'm also Microsoft MVP. Thanks, Microsoft. And I'm an Ed user group Zurich co-lead along other friends of mine. I founded it in 2012 when I arrived in Switzerland, and I'm happily hosting events which are quite cool. Today we are doing another one, also machine learning related. So what's in for today? We are going to do a quick refresher on AI. because I expect that the audience are mostly developers. So maybe you don't know about AI, or maybe you have a bit of AI, then, well, that will sound familiar, but it's always a good refresher. That will take about, it will be quick, fast. And then we will jump into Azure Machine Learning. We will see what is it, how it integrates with Azure, and we will take a look at the different flavors, the designer, auto machine learning, and the notebook experience. Last but not least, we will take a peek at what is ONX. That'll be quick, I promise. And at the end, my promise to you, it's very daring. You will understand what Azure Machine Learning is, and you will know how to create models with Azure Machine Learning. So let's get started. AI refresh. AI started as soon as we could program computers in 1950. It's essentially the ability of machines to mimic human behavior, intelligent one. Later on, it came what we call ML or machine learning, which is the ability of machines to make predictions and inferences based on its experience, which we know its data. That came a bit later, 1980. And then we have the star of the show as of today. This is deep learning. Deep learning is the ability of machines to learn upon mimicking the human structure, exactly what we have in your brains. It's called neurons. Some of us have them, And then as well to mimic how they are layered inside of our brains and enable as well the plasticity and elasticity of the neurons. That started in 2010. Even it was, the concept was there before, some trials were before, but we never had the computing power that we have today, and it's drastically increasing. Then, how do we train a machine learning? We put some pictures or information, we label them, we train the model, and then the model can see that image in this case and detect. Let's see it again. We label them, we train a model, the model is deployed, and then the model sees the picture and can say, oh, this is this picture. Machine learning algorithms have essentially three categories. Big ones. Supervised, that's the one we just saw. This is information or data that we have put a label. Label is normally what we want to predict, the label or a number. In this case, we wanted to predict the name of a flower. If we want to predict a price, we put obviously a number. Then we have unsupervised, which is we don't put anything and the machine does everything. How can it work? You're probably asking yourselves. It's easy. It analyzes the data and takes different points of view and determines similitudes on the data. And essentially, the only thing it can do is group similar data together. And then we have reinforcement. That's kind of a bit of the star as well. This is what enables computers and machine learning algorithms to beat us at our own game, like chess, Go, I would say even image recognition, and other things that were appearing. So at some specific things, they are really better and faster than us, way faster and precise, a lot more precise. Well, how does it work? How can we get a model that is better than a human or close? This is what we call the machine learning workflow, and usually it is like I'm showing you. We have what is the data extraction. This is called ETL, extract, transform, and load. Sometimes they say extract, load, and transform, but at the end it's just preparing the data so a machine learning algorithm can understand it. It's ready for a computer to analyze it. Then we train the machine learning model. So we pick a model and we train it with that data. And then we select and deploy the model. Once the model is deployed, we can feed it a known data and it can do a prediction, also called inferencing. And the end, we get a prediction. And that's essentially how it works. We have a training phase and then we get that model. The model is like a brain in a box, small brain in this case, and we simply use it for doing predictions. Nothing more. That's it. That was easy. I think it was like a few minutes, 3 or 4. And we get into Azure machine learning. That's the big promise of Microsoft for a data scientist or a developer that wants to do machine learning. This I'm showing you is the main slide or marketing slide, which is essentially says that Azure machine learning is to bring AI to everybody with an end-to-end scalable, trusted platform, secure. It essentially will boost your data science productivity, increase your rate of experimentation, will make you better data scientist, and help you to deploy your models everywhere, mostly in Azure Cloud, I would say, but yeah, essentially it can do that everywhere. And then it's built with the needs of a data scientist in mind. It enables a lot of things which are really, really uber cool. Automated machine learning, managed compute, simple deployment, DevOps for machine learning, also called MLOps. We're not going to talk about that today. It has support for open source frameworks, mostly, I think the most popular are already included, and has a tool agnostic Python SDK. And yeah, it's pretty integrated with the Azure portfolio, while the previous one, the Azure Machine Learning Studio Classic, was not. But let's get a bit into it. I would say that Azure Machine Learning has two parts. One, I would call it, its proper name is the workspace, but I would call it the backend. The backend is what usually you will not look at it, but you need to create it before you can do anything. That's the Azure Machine Learning workspace. The workspace is in the middle, and it creates some dependency to some Azure elements like a storage account, container registry to containerize and to put in like small packages your models and services that wrap them, Azure Cable for storing your secrets, and Azure Application Insights for doing monitoring and logging. And then it has some link services to data stores and compute targets, and enables us to create and manage some resources like compute instances and compute clusters that they are specialized to do the inferencing and training of the model for us. That's really, for me, the most amazing thing that we have here. Then we have some other assets that we can use in the portal, which are environment, experiments, pipelines, datasets, models, and endpoints. We will take a look at them in a moment. Then we have the studio, Azure Machine Learning Studio. That is the UI, the front end. It has a set of Azure Cloud services that we can use in a transparent way. We can use the Python SDK behind the scenes without even noticing, unless we are using that directly with a notebook. And that enables us to prepare the data, to train and build the models. Excuse me. Manage the models, track experiments, and deploy the models. That's one of the amazing things here is that this is completely multi-user. So this is meant to be used for a team. So you can share, or you can look at the same code that your colleagues are working and annotate them. That's recently enabled. That's pretty awesome. So first, how do we get there? And as we are developers, and I think it's better that we take a look to that. Let me go to the portal. So you are seeing the portal. This is the Microsoft Azure portal, which you can go to portal.azure.com that say you should have an account there. You can create a free account. If you never use it, it's fairly easy. And then the only thing you need is to click on create a resource when you are in home. So now we are in home. You click on create a resource and you put machine learning. You can enter, of course. We have a selection, and usually the first one, machine learning. This is the machine learning workspace that you will create. Once we click on create, you can select a resource group. I have already a WeAreDevelopers Machine Learning Day. You put a name, and it will propose a region. This is my default at the moment with Europe. If you are in Switzerland, you could choose Switzerland or any other that is closer to you. The closer, the best, the better, faster. And then you create a storage account, a cable, application insights, and container registry. It's optional. So if you're not going to deploy, which we aren't going to do that today, you can avoid that. Then you can set some networking and advanced tags, and then you can simply click on review and create and go ahead. In this case, I have already created one, so you don't have to wait. And you can hide these and hide these. So here is a resource group, which is kind of a folder. I created this machine learning workspace. Even the workspace does not appear. And here are these, the ones I mentioned, the analytics, keyboard, and the storage account, where simply we will store everything that we want to store. On the machine learning workspace, if we click here, here is where we can manage access. We can give grants to our peers. Usually that's done by an administrator, by an IT person. If you're a data scientist, you don't have to worry. If you're a developer, probably they will ask you to do it. And then you launch the studio. The machine learning studio is the front end that we saw. I'm closing that one. Here we are, Machine Learning Day 2022. Here I have created already a few things. As I don't want to make you wait during this presentation, but that's it. So the first thing is to do a bit of an overview. This guided tour is pretty cool. I like it. I recommend if you do that to do it completely. Here, Azure Machine Learning Studio enables you to register data. Once you have the data in the studio or link in the studio, you can train the models and then evaluate them and deploy. We're going to go until the train model part today. And it has several sections. First is what I call the 3 flavors, which you can use to create a model. So essentially, you have the notebooks, which is kind of have like kind of what would I say? Jupyter notebooks is the proper term where it comes, but essentially this is like kind of declarative computing where it mixes text and code, and it helps really, really a lot. We have as well automated machine learning, which is using, to me, it's a fantastic thing. And then the pipelines, which are essentially also what we create. So we are creating like a workflow, and this is stored here in the pipelines. At the end, we have, next we have the environments. Environments is like a ready-made environments of a concrete library that you want to use. It enables us to reproduce exactly an environment. Then you have the models that you have deployed, and the endpoints, which is the way that we access our models. So everything is under strict versioning, under strict monitoring, and it's pretty cool. And then we have also compute, which we can define a virtual machine to do machine learning. So you don't have to use your own. And more important, you can set up a really, really incredible machine in there and use it for only training the model when you need it. So you pay only for what you use and when you use it, which is pretty cool. And you can create a cluster. We will do that in a moment. And you can define data stores for keeping your information, and then link services for accessing external services, and data labeling. I believe at the moment this is only for image, like the example we saw for classifying an image or several images to understand, okay, this is a Bellis perennis flower or another. And it's regarding text, it's on preview at the moment. And that's about it. One thing we should do at the beginning, I already created some compute instances and some compute clusters, is to create them. So if you're following along, I would put, you could put, for example, going crazy. Let's do a GPU. You have some options. Here, usually the available quota you will have is 6 to 10 cores. So you have to open a ticket to order more. But, well, you could go crazy and say, okay, I want like 12 cores, 100 gigas of RAM. Seems, oh, I don't have that for this. So you could ask even for this. And you have access to GPU devices which are really, really powerful. Like, for example, this one. You could then click on create, and that would be it. But I'm going to leave because I already created a compute node, and the cluster is exactly the same. You select where you're running. You want a dedicated or low priority CPU or CPU or GPU. GPU is better for neural networks or deep learning. And you have a lot of options which are really, really powerful. So you could go for 48 cores, about 400 gigabytes of RAM. Well, things that you probably will not have ever in your home. And this enables you to have that just for 1 or 2 or 3 hours when you're training the model, and that's basically it. So this is everything you need to get started and to get your Azure Machine Learning workspace and studio ready with some computes to work. That said, if you have a cluster, if you check at the moment, it's 0 nodes working, but the compute instance is always running. So it's better if you don't use it to go and click stop or delete it. I usually stop it if I have to use it along in 1 or 2 days. Otherwise, I delete it and create it anew. Just some recommendations. Again, let's take a look now at the 3 different flavors. So I'm going to check the machine learning designer. That's a drag and drop experience, which I particularly love, as it was how I began a bit in machine learning with the Azure Machine Learning Studio, the classic now. Remember, because it's still available. I believe you can still create a workspace. I'm not sure if you can, but it's going to be deprecated in 2024. So I would not use it for production, just for curiosity. So let's take a look at the designer. We don't need that anymore. And let's go to the designer. So I have already one created. I'm going to open it and explore it. This is a drag and drop that usually you don't see this section. Also, you can hide this part, which is quite convenient. And the way to work, this works is you have, for example, some sample data sets and automobile private data. You can simply drag and drop it. I have done already, but just wanted to show you how does it work. And then you can go on data transformation. You can say, okay, I want to clean missing data and drag and drop it, right? Or you can simply search clean missing data, for example, and then you can drag and drop it. It's really very useful. And it works really from top to bottom. So you start with the data and then it flows down like a river. You can click on the different parts, see some information, configure it. You can preview the data, make it bigger, analyze, see if everything is good, everything's bad, observe a few things. Then I simply here select some columns, and I'm excluding these normalized losses, which you can simply include all columns, exclude column names, and I'm taking these normalized losses, which is pretty useful. Because ahead, so it's pretty cool and useful. Then on the clean missing data, some of the data was inconclusive, so was some parts of the data were not labeled or had no value. I put that I clean all columns, and if any column doesn't have a proper data between 0 and 1, or I remove the entire row. And then here you can see the clean data. So that's also pretty cool. I could preview the data, 205 rows, and after cleaning, I think it's 193 in this case. So let's clean that up. Then I do the split of the data. This is part of the TL. So some parts of the data, which is labeled. So to show the data, if I show it at the end, we have the price. And we want to predict is the price, not a label, but a price at the end. And then we split. This split, I'm doing 70% will go to training the model, and the rest will go to score the model or verify that it worked. I pick a model, which is linear regression, simply statistic function, and then I train it with the data, with experience. I'm giving experience to the model, training the model, and the output is the trained model, and then I score it with the 20% of the data that it has never seen. And then I evaluate it. On the evaluation at the end, we had some metrics. And one thing to look here is the coefficient of determination. There are several ways to do that, but this is one of the best metrics for this. And as close as to 1 is how it works the best. There is like a distribution on the mean square error. So the different points of the data are put and squared and added together. So, but the relative square error is the similar information, but normalized in a way that the closest to 0, the better. So this is our train model. One thing to say is that if we click in this wheel, we can configure it. At the beginning, we will need to assign either a compute cluster or instance. Oops, I lost it, sorry. And I selected the WeAreDevelopers cluster, which is 16 virtual CPUs, 112 megabytes of RAM. Yeah, that's a bit overkill, but yeah, it was good to do that. That said, once we run these, we can take a look at experiments. And I create the experiment, which has this name, Designer AutoML Prediction Experiment 01. And if we click at it, we can see a bit of details of it, how many rounds. We can see the child rounds. We don't care about that now. So, and if we click there, we have a snapshot of the designer pipeline that we built. Here we see we had an untrain, here it's train, and it tells that what is the input and the output and what happened every time. It's really, really pretty cool. And at the end, we have that. And we could have some explanations, but this is in preview. Sometimes it's not working that well, but let's take a look. No. So it's not in there. I'm not going to generate them at the moment. And we will see when we jump into automated machine learning, which should be in a moment. That's it for designer pipeline. Then we are jumping into auto machine learning. That's essentially machine learning to create machine learning, to do everything for us. Everything we did now, but even better, it's done automatically for us. It will do the feature selection, engineering. It will implement the concept called the data guardrail. So if some data is really not good, it will check it and tell us. Sometimes it will fix it himself. Sometimes it will not. And then it will select the best model for us, do the hyperparameter of the model for us, and then even provide the explanation of the model and give us insights to what is important, what is the feature importance. Then it will support different tasks like classification, regression, and time series. Just say it, last week it was announced by Microsoft. I guess it was an announcement by Cesar de Latorre, which is the person behind machine learning in Azure, that language services is released for auto machine learning, which is pretty cool. At the moment, you can do that only with notebooks, but probably it will reach the UI. I really don't know. I'm not aware of a roadmap, so at least now. Then what's cool as well is it supports time series. That's pretty powerful, and it's essentially data scientist in a box. So it will do all the work that machine learning scientists would do for you. And it's essentially the dream of an aficionado data scientist if you don't work. So essentially, it works like that. It does a feature selection of the data. It trains in different models, checks which one fared the better, selects it, and then it optimizes the parameters for execution of the model and gives you an optimized model. At the end, the only thing you have to give it is a data set, a target metric, and a constraint. So you can tell it, hey, I don't want this to take more than 1 hour or 2 or 24, right? And it will give you a scoreboard of algorithms that you train, features, the parameters, and at the end, the precision, and give a final leaderboard of the best of the best it could do. It's simply that amazing. I'm going to show you that to you in a moment. So let's back to the portal. We go to Auto Machine Learning. I play a bit with that, but I'm going to show you how you create a new Auto Machine Learning run. It's essentially a wizard. So you configure it and you play next, and then you have just to wait for the result. So first, you select a data set. I have already created one. You could create it one for local files, data store. This one is from local files. It's a CSV file. Essentially, you import and it's next. This is a bank marketing data set. So it has information about persons that enter bank and the outcome of what we want to predict if they purchase the product or not. Having selected it, I will have to configure the run. I can put a name. I will not run this. I will select the text column. So as you see, is information about the people, marital, education. Oh my God, the banks know a lot about us. And the end is a yes. This is what is the level, what we want to predict. This is what the model will be trained to predict. And then the compute type. It's here it's recommended that you use a cluster that can scale. And we will select the nice one with 16 CPUs. And once we click next, it will choose for us the type of machine learning. Sorry. And you can enable or not deep learning. For that, I recommend you pick GPU-based virtual machine, which is pretty convenient. And then you can configure some additional settings, like the metric it will use to determine the precision. If you don't want to use a model, you can say, oh, I don't want the KNN, for example. And configuration, you could choose a positive class level or training job. You can say, okay, 24 hours maximum. In this case, I run it with more or less 1 hour. I'll show you. And you can also tell it, okay, when it reaches 95%, it's good enough. I'm happy. And it finishes the training. And the max concurrent iterations. By default, it's the maximum number of virtual machines in the cluster. Then you can save it. And next, you can run it. I will not run it because I already did for you, so you don't have to wait. And if we go back to experiments, we will see it. As I give it the proper name, this is a name I gave it. It's AutoML Bank Marketing Experiment. By the way, the runs are sub-iterations that are done for us, and this can be hierarchical. So a run can have many runs, and an experiment can have many runs as well. And the runs are given like very funny names automatically, so that I find it very interesting, like NITRAC or Oldenboot. If we go to the machine learning, we will see that it's completed. It took 30 minutes. And if we include the child runs, well, some of them even were canceled. So Auto Machine Learning has the ability to stop when it sees that it cannot progress or evolve anymore. And if we click on it, then we will see the proper run, the main run and outcome. This is pretty awesome. It chooses the algorithm name. In this case, there are two, standard scalar wrapper XBoost classifier. And we could even check the upper parameters, and it reads like a AUC of 0.94, which is, we could read it more or less as 95% of precision. I know that's, if we talk properly, that's absolutely wrong, but you can read it like that. And it simplifies a bit the thinking. And it's essentially pretty good. If we click on the data guardrails, it has detected the class balancing detection. It detected some imbalancing, and we could look into that. So we could improve the data and fix it. But the models are not bad at all. Here we have the rating that we mentioned. It trained 56 models or iterations of them and selected this one, this standard scalar wrapper classifier. And it even can give us an explanation. That's really awesome. on the explanation, it gives some insights of the data and gives, for example, what is the criteria that are affecting more the decision of a customer to buy or not the product. In this case, it's interesting that the more time that the person stays, it has a correlation, clear correlation. And then if the person is employed, or the variability rate, and also some other parameters which depend on the country, which is like Euribor or variability rate of the market. We could even see a bit more, but they are even affecting a lot less. But yeah, that's pretty cool, because it tells clearly to the bank that, okay, you should get people that know how to talk, and maybe invite the customer to a coffee, maybe a croissant as well, and they will stay a bit more and raise the chances of, customer signing the contract. And then you get a lot of other things, apart from metrics, a bit of graphical representation. It's pretty cool. That's essentially automated machine learning. At these moments, the models, you can get them, they are internal, but you can also deploy them and export them. It's pretty cool. In regards of notebooks, what can I tell you? Oh, no. It's time to go to the portal again. So we are not leaving the portal almost, which is good. When you start, usually this part is empty. And what I did in this case, I got some samples. I got exactly this tutorial. I think it's pretty cool. And I opened this ePyNB, which is Interactive Python Notebook, and I click on clone this notebook. I'm showing that to you because one of the best ways, or mostly the most important way of learning is doing. So you can do that. I recommend after the session, you go and play a bit with that. So I go and click clone. I have already done so, and I don't want to rewrite. So I go back to my files. I go back to here. These are also some details of the run, and I have this regression automated ePyNB, this Python notebook. And at this moment, I can hide this and this, so the view is less cumbersome. Usually, you will have that selected, or otherwise you have to select it. And this is the compute associated to that. And this is what we call a Python notebook, or a notebook, and it's essentially a mix of text and code, which we call its markdown. So if we click here, you can see it's basically like typing code with some characters that are transforming a nicer visualization. Also, we can use like, this is, for example, to determine like the title. And then we have the code here, and we can simply run the cell, or if we click here, we can run all the cells below, including this one, which is pretty cool and convenient. I did that yesterday to prepare for this session, and I'll go pretty quick here. And here it's essentially Python, and I'm getting some libraries on it to work with it, some from Azure, some normal in Python like pandas for working with data. Here I'm getting this data set, which is already on a blob storage. This is the green taxi dataset. I believe it's from New York, and I guess it's from some days. I get the head, I get the data frame here. So I visualize a bit the data and see that there's some things that I don't want to use or are simply too much. And I'm simply removing them and cleaning the data. So usually a lot of data science is to prepare the data to train a model, to get it ready. So it's sometimes 60 or even 80% of the work, which makes this not that exciting. Also good, because if you want to do good machine learning, you need to know your data really, really well. Then what we do here is we have removed this payment type for amount, tip amount, etc. And at the end, the only thing we want to do here, which is also important, is to predict what is the cost of the taxi. So the total amount. And usually we only will get the passenger count and the trip distance. Also important, the pickup longitude, latitude, but we will get rid of that in a moment. So one thing which is pretty cool is to do the describe. Here we can see some statistic information like the minimum, mean, maximum, and that tells a lot about your data and if it makes sense or not. For example, having a passenger ride of 0 persons does not make sense. Having a trip distance of 154 in New York, where the maximum diagonal distance is 30, also doesn't make any sense. So we have some outliers that don't make any sense, like having no longitude or latitude that does not belong to the city. So also doesn't make any sense. So what we do usually is this data that can destroy our predictions, we get rid of them or we clean them. Here we are checking that all the taxis are picking somebody inside New York, Manhattan, and then that the trip distance is over, I think 200 meters, and the trip distance is smaller than 31. I think 31 or 30 is the total distance. And the passenger count is greater than 0. And the total amount of money is also greater than 0, because we had that as well. And then we remove the longitude and latitude coordinates, which we don't need anymore. Once this is done, we have data which is perfectly valid, and we can configure everything to run the same as we did before through the UI. So we are doing auto machine learning, but we are doing it with code. So we import the workspace. We are preparing the test split. What we did in the designer, we put for testing 0.2, and the random is like a random number that serves as a seed to randomly put some data in the training set or the test set. On another part, here are some parameters that we gave it before on the UI. So we have the iteration timeout, the experiment timeout. This is curious because in AutoML in the UI, the minimum timeout is 0.5, and here is 0.3, which is curious. Here is the metric. If we want the filterization to be automatically, I want to provide it, and we put that in code. As well as we generate it and we put it into an auto machine learning configuration, including the logs and the column that we want to predict, which is the total amount. Finally, we set it to train the model. And here with this Azure Machine Learning, we create the experiment, which is what we do when we click on Start the Run, and we name it Tutorial New York City Taxi. And we execute it. This will generate and try several models, and they are shown visually. One thing which is important is when you are running, don't get away from this. This is interactive. So if we close it, it will understand that you no longer want to work with it, and the experiment will still run, but you will get no results in your Python notebook, and that's not good. At the end, you simply get the results, you get the best model that you got, and you want to validate it, and you will predict it. Like, for example, for 10 values. And at the end, you simply do a bit of a mean of the different executions, like 10 executions, and you get, for example, this model accuracy. In this case, it was not that high, 0.69, but it's not that bad. Also, the outcome of this, you can see in the files. So you can get the logs and the different runs. And I think one of them, or both of them, you can even explore and check. And the model is there, and you can deploy it. You could also export it as auto machine learning. You need to do some tampering in there, but so far is pretty cool. All right. On the experiments, this tutorial, New York City taxi, here is the execution. I think there are 2 executions that I perform. Let's take the last one. And you can check that what won the prize on the auto machine learning is the voting ensemble. If we go to the models, we could see this is here. If you don't have an explanation, we could, all right. Sometimes you select it and edit columns. Yeah, we don't have the explanation. Usually you can generate it by clicking and generate an explanation. But I guess that's only on automated machine learning at this moment. But you can also check the algorithm and see it a bit with more details, which is pretty cool. All right, so that's basically it. So ONX, what is ONX? ONX is the new format for machine learning, in my opinion. So it stands for Open Neural Network Exchange. That essentially is that you can import and export a model, like a package model, like a zip file, everywhere, and it simply will work. You can do that in your computer, either it's Windows, Mac, or Linux. You can do that essentially everywhere to your mobile device. You can do that in IoT, in the edge, basically everywhere, and it's simply awesome. Almost everybody is using that, either it's a deep learning framework or a tool, like for example, Azure Machine Learning is doing that extensively. It's adding that. It started in the collaboration of Microsoft and Facebook, now Meta. Yeah, I think it's pretty important to keep an eye on ONX, and I believe that this is the future of machine learning deployment, because it also optimizes the algorithms for the platform they will run in. So, for example, the digit precision, it's automatically optimized, and there are other optimizations. So it will always optimize to the platform it is executed for inferencing. So it's a pretty amazing standard to support and give your love to. Apart from that, that's it from my side. I'll give you some links and feedbacks. I will send the organizers this slide, but the main takeover is Azure Machine Learning rocks. It has everything that Microsoft promised to us. So their marketing slides are absolutely true. And that's my personal opinion. I don't work for Microsoft, as I said. It has everything we need to create an inference pipelines, deploy models, and do that at the scale and in a team even more. The designer, machine learning, for auto machine learning and notebooks are really cool. They work really well. You can even configure them with environments. It supports ONX at the moment only with notebooks. And the best, of course, if you try it yourself. I left some feedback there, like Microsoft Certified Data Scientist Associate, AI Fundamentals. These are 2 courses on Microsoft Learning, which are really cool. I recommend you to check them if you're curious. And then this is a tutorial on build and operate machine learning as well in the tutorials of Microsoft Learn, which are really well done. So that's basically it on my side. I'm open for some query and answer if you would like. Thank you. You're muted, Benedict.
Thank you. Second time this talk. Jose, thank you so much for the interesting talk. Welcome back on the live stage. I hope you had fun.
I did.
Presenting. So let's jump right into some questions. Maybe also to you, how did you get into machine learning yourself?
I've been always curious, and some people say it's smart, but I call myself sometimes lazy, so I like to make computers to do things for me. And I think the concept of a computer acting like an intelligent human is quite cool. And even more today, that we can get computers to do things at a faster pace and higher precision than some humans.
All right. Yeah, maybe you also want to tell us about your first computer, your first machine.
Yeah, sure. My first computer was mine was an Auric Atmos, which was about the time of Spectrum, the ZX Spectrum. And I learned with it by hacking the code. So it's about that time that you were loading a computer with, a cassette, right?
Yeah.
And you were hearing all the wee sounds. That was really cool.
Different times, yeah, different times. So
Yes.
you showed some links and sources at the end, but is there any other material you might want to add, like books, blogs, YouTubers, something like that?
Blogs. I think at this moment for machine learning in YouTube, I would point mostly to Microsoft Reactor. They are doing quite cool events. I would point as well to Microsoft Learn. They are keeping the information quite up to date there. And to blogs, I'm not really blogging. I have a blog which is Azure Samurai, but I'm not blogging too much about Azure machine learning. But probably I will. I want to, but finding time is another thing, right? And yeah, these to me are the best parts. And definitely the link I gave it before, my GitHub, I will put there the link and the presentations. I will give them to you afterwards.
Okay,
so if you want to publish them.
Much. So maybe another question from Roland. What were some cool projects that you used AutoML for?
AutoML, I'm probably using it to try to determine and play around with some time series prediction, which I found this really, really interesting. So one of my private projects is I want to start investing this year, and I'm playing a bit with that. Even probably it's not the best moment, or maybe it's the best moment. Well, so I'm just playing around with some public data sets for that, which are openly like the stock market.
Sounds interesting. So another user wants to know, do you think a data science knowledge or background and education is still needed to do this job, given all these tools?
That's a really good question, because as I show, AutoML is doing a big part of the job for us. But if you want to go further, then yes. If you want to get into fine-tune a model the best possible way, and your company depends on that, probably you will end up having a data scientist, because it's a key part in there and you want the best. Right, and probably all the other companies will be using this kind of ready-made, out-of-the-box algorithms. Today, it's easy to use machine learning. So, for example, the other thing that you have in Azure is cognitive services, which are mostly out-of-the-box, ready-made, ready-to-use machine learning algorithms, and they work really, really well. So I've been playing last week, for example, with the language one, and it's simply amazing. It's simply that good. It can detect the language. It can detect personal information, which is good for, GDPR things that if you work in a company, you probably know or suffer. And it can really do automatic censorship. So you have, for example, a phrase, "Hi, I'm John, and my SQL security number is 12345. That's fake, by the way. And I'm interested in buying a Ferrari, right? And you get back, "Hey, I'm asterisk, my social security number is asterisk." So everything is censored, and you can be sure that you can get that data and upload it to a database without infringing any GDPR law.
Okay, very powerful tool indeed. So I think your talk was almost too detailed, as there are no more questions left. But I know that you are occupied later. Would you mind telling us about something?
Yes, of course. So, all right. Sharing the screen.
Yep.
All right. So, as I mentioned, I have a passion, which is developer communities, which I happen to do also at work. And out of work, I also commit myself to a community which is called Zurich Developers User Group, Zurich.net Developers User Group. And today we are talking about machine learning as well. So we have the machine learning day later on. At 6 o'clock, we will have 2 sessions, C# and machine learning.net, and object detection with machine learning.net with 2 awesome speakers. So yeah, the link is there. I think, I don't know, I will add it in comments. I know. Don't know if I can.
already posted it in the chat.
Perfect. Thank you.
Thank you, Gary.
Yeah, thanks to you. It was a pleasure to be here with you. Such an amazing host, such an amazing platform.
Yeah, Jose, thank you so much for your talk. Thank you so much for your time, and hope to see you soon, maybe on the next topic day.
Could be. That would be my pleasure.
Bye.
Have a nice day.
Thank you, you too. So, and now that we are almost at the end of this live session, quick reminder to go to worldcongress.dev to get further information on our World Congress in Berlin in June and buy your tickets. Also, quick reminder, in 2 weeks on April the 6th, our Cloud Day will be exactly at this time, at 10 a.m. Central European Time. And we have 4 speakers, very interesting. So make sure to register for free on WeAreDevelopers.com. Okay, so now all that is left to say, thank you very much for your participation. And thank you so much for being in our community. I wish you a very nice day and hope to see you soon. Bye.
Good morning,
Everything is being influenced by code written by developers.
At some point, you're going to wake up and say, what the hell am I doing?
It's hard to believe. It's the largest group I've ever been in front of, I think.
We develop the future.